All right, in the previous video that you watched, you saw how what we've been doing up until this point kind of graphically looks like taking a line and finding the rate of change for a function using that line and 2 points that are sort of far apart, and then moving the 2 points closer together until you can get a really good approximation of that rate of change. Well, guys, I hope you understood that he was talking about limits there, which we've seen, but we're also going to talk about that in terms of what we call finding the slope of the tangent line. So what he showed you in the video was something that looked like this. You had 2 points on a function, and you found the rise over run of those 2 points. Now the difference here is we're labeling these points a little bit strangely. We've got the x-coordinate, and we've got what you would get if you plug x into your function. So we call that f of x. That's the output, input, output. Well, if we move our x-coordinate to the right a little bit, that gives us a brand new y-coordinate. So the x-coordinate has moved right, h, and then we add in h into the output when we find it as well. So our slope becomes this value over this value. So when we're looking at what we would find as the slope of that secant line that we see on the picture there, it's just whatever that value is. We don't actually have an exact value for it, but it's f of x plus h minus f of x over h. Okay, so as we move that, now we know what this is. I think that you guys probably recognize what I just wrote based on what we did last week, but we're going to keep playing with this a little bit. If we continue to move that point wherever we had h, if we continue to make h be closer to x, okay, and this second point, if we continue to move it a little bit closer, and a little bit closer to the original point, what happens is this difference between the 2 points, which we called h, is getting smaller. In fact, it's getting smaller and it's approaching 0. And when it actually reaches 0, that's our tangent line. So what we're actually doing here is as we move h, again, which is the distance between the 2 x-coordinates, closer and closer to 0, the secant line will approach the tangent line. And this gives us a way to find the exact slope of that tangent line. It gives us a way to find the instantaneous rate of change. And that instantaneous rate of change is found by taking the limit of the secant line as h approaches 0. The limit of the slope of the secant line as h approaches 0. Well, we found out on the previous page that this slope of the secant line was this quantity. And when you put all of that together, the limit as h approaches 0 of f of x plus h minus f of x all over h, well, that looks really familiar. That is exactly what we were talking about last week. So we were able to actually use what we were doing last week to find the slope of the tangent line. So I want to go ahead and do that with you just as an example to make sure that we're all on the same page here. We're going to do 2 examples together here. We're going to find the slope of a tangent line to f of x equals negative 2x plus 4. Okay, so how do we find the slope of the tangent line? Well, we use our limit that we talked about last week. The limit as h approaches 0 of f of x plus h minus f of x all over h. And what we did last week is we said, okay, well, if f of x is negative 2x plus 4, then f of x plus h will replace the x with x plus h, and we get negative 2 times the quantity x plus h plus 4, which we can simplify to be negative 2x minus 2h plus 4. Now, if you remember, if you were in the Google Meet session last week, you saw how I kind of color-coded things. okay? And I think that makes it a little bit easier to understand what goes where. So really what we have here is the limit as h approaches 0 of, and then we take f of x plus h, which is negative 2x minus 2h plus 4, and we subtract f of x, which is negative 2x plus 4. And then we have this expression that we can go ahead and simplify based on our algebra skills. And this part isn't really difficult necessarily. Negative 2x minus 2h plus 4, and then we'll have plus 2x minus 4 all over h. And we look for those things that are going to be 0 when we add them. So things like negative 2x and 2x are 0, 4 and negative 4 are 0, and then what we're left with is just the limit as h approaches 0 of negative 2h over h. And then before we do anything, we have a giant 1 here. Okay, so I get rid of that giant 1, and I get the limit as h approaches 0 of negative 2. Now, we know that this is a constant function. Okay, it's going to be a horizontal line going through y equals negative 2. And the limit as h approaches 0 is there's no h to plug in, basically, is what it comes down to. So our limit of a constant function is just negative 2. Now, what's interesting about this is that we did not specify anywhere on that original graph where we were finding the instantaneous rate of change. So what this actually is telling us is that the instantaneous rate of change anywhere on that graph will be negative 2, no matter where we go. And that fits with what we know about lines. The slope of a line is really the average rate of change, or the instantaneous rate of change for that line is always going to be the slope, which is negative 2, as we can see in the original function itself. Okay, let's try example 4 and see how this goes. All right, so we're going to find, again, the slope of the tangent line. So we're doing the limit as h approaches 0 of f of x plus h minus f of x all over h for our function, f of x equals x squared. Again, it's helpful here if we know what f of x plus h is. So I'll plug in x plus h wherever we had x. And then based on what we did last week, I'm hoping you guys should recognize that that will simplify to be what you see on the screen there. So just again, I'm going to highlight some things. Let me use a different color instead of green. That was hard to see last time. So we can easily find them, and then I'm going to start plugging things in. So I've got the limit as h approaches 0 of f of x plus h, which is the x squared plus 2xh plus, h squared, minus f of x, which is just x squared, all over h. And once again, I've just got to go through and simplify some stuff here. So I've got the limit as h approaches 0, and then what I see are x squared and minus x squared that are going to be 0 when you add them together, just leaving me with 2xh plus h squared all over h. Okay, so then I can, if you remember our process from last week, we always got to a point where we only had things that had h left in them. So I'm going to factor out an h so that I get my giant 1. And I have 2x plus h as my limit. Now is when I can go ahead and plug in 0 for h. And I'm going to get 2x plus 0, which is just 2x. Now, let's just stop for a minute and talk about what this is. 2x is a way for us to find the instantaneous rate of change anywhere on the original function. Okay, so that instantaneous rate of change is always going to be 2 times x. So wherever we are on the graph, imagine your graph of the x squared function. Okay, let's say we pick a point here, 3, 9. If I want to find the instantaneous rate of change, I'm just going to take whatever that x-coordinate is and plug it into what I just found. So 2 times 3 is 6. That's my instantaneous rate of change. Now, I gave you a specific point, -2, 4, to actually use. So the instantaneous rate of change is just going to be 2 times -2, which is -4. This is the slope of the tangent line at the point -2, 4. We could also think of this as the instantaneous rate of change at the point -2, 4. Okay, so there's a couple ways we can think about that. All right, so go ahead and use this information, try a couple of problems in the Google form, and then watch the next video.